how to tackle these questions. So this example is one of the previous exam questions. So from this example, you can evaluate yourself to see how well you have learned for this part. So the problem formulation is we try to maximize the cost function given by Vx. TF, where the TF equals to 10 seconds. So we want to maximize this velocity in the x direction with the control input of u. So subject to dynamics of the system. So the dynamics is quite standard. A standard dynamic in the 2D space. So the x dot equal to Vx. So the location, x is the location, the Vx is the velocity. So the location, the derivative of the location gives the velocity. That's the standard and the simplified dynamics. So the y dot equal to Vy. The Vx dot equal to defined equal to cosine u. And the Vy dot equal to sine u. And the initial condition is given by, so this x0 is 0, so the initial position is 0, and this y0 is 0. So the final condition is this x10 is free, and this y10 equal to 100 meters. So these are the problems that we want to tackle. So we want to maximize this cost function just given by the final velocity in the x direction, the Vx. We want to maximize the velocity. And subject to this set of dynamics of the system. We know the standard dynamics given by this x dot equal to Vx, y dot equal to Vy. So the Vx dot equal to u, some kind of u, a function of u, and the Vy dot also in relation to the control input. So the scenario for this problem is like this. So assume we have something to cross. So for example, we want to cross a river. So the width of the river is 100 meters. So that's why we have this final condition where the location in the y direction is 100 meters. So we define the coordinate like this. So these are x. These are our y coordinate. So assume here is the 0 point. These are the 0. So the x is 0. So we have this x0 equal to 0 and y0 equal to 0. So these are the 0 point. So we have this x and we have this location, this direction y. So this problem is require you to apply proper control input u, control input of the u, in order that so you can cross this river because your initial location is at 0, and the final condition is the y condition, the y position is 100. So you will be somewhere at here, already cross the river. But the x position is free. That means you could be in any position along this line. So for example, you apply some control input. Eventually you make some trajectory like this for your mobile vehicle, but eventually you arrive at here. So when at here, you got your Vx, you got your velocity in the x direction. So this question is asking you to maximize this velocity. So these are the problem formulation. So this question is one of the previous exam papers. So from this question you can see technically the exam questions are somewhat different from the examples, from the lecture examples. And it's a little bit flexible. So you should be able to fully understand the theory so that you can apply the techniques to this problem. So later I will show you the solution. From the solution, once you know the solution, you will know actually it's quite straightforward to solve this problem. But before I show the solution, maybe you think the question is very challenging because you have no idea to tackle this problem. So this course involves quite a lot of mathematical derivation. So it's probably one of the most challenging modules that you have done so far. But if you have a good background on mathematics, you will find it's quite easy. The solutions to this problem. So just now we discussed the problem formulation and the solutions. So up here you see, if we want to establish the Euler-Lagrange equations, we have to construct this Hamiltonian. So the Hamiltonian will be given by this L plus linear combination of the cost functions, of the constraint functions. But in this equation also identify this L. Also identify this L. So this is one of the first problem that we are facing. So remember that when we derive the equations, we augment the cost function. Remember that when we derive the equation, we have an augment. This cost function is given by the original cost function plus this lambda f. So we ever use the same equation in the constraint optimization problem. In the constraint optimization problem, we use the same equation. But in this part, this equation will be slightly different from here. So essentially, the augment cost function is given by this final state. We know we are not going to augment the final state. So this final state needs to be copied at here. The Vx f. plus. So here we know we actually got, so this equivalent to is plus integration from T0 to Tf, but it's a 0.
So
It's a 0. It's a 0 dt. So we know this integration will be equal to 0. So actually, if we have this equation in this form, we can see now the equation is quite similar to this format. So now we can augment the equation within the integral. So integration from T0 to Tf. So it's a 0 plus. And remember that our idea to augment the cost function is to maintain the value of the cost function at the optimal value, because this part is f equal to 0. Or in order to distinguish this f from the f used here, we can define this f to be a capital F, the capital F. So in this case, this capital F. So for example, our first one is x dot equal to f1, x dot equal to f1. So we can change this equation into f1 minus x dot equal to 0. And we can define this part will be f1. So in this case, we will use this f1 to augment this cost function because this one is 0. So the cost values remain the same. Is that the idea? So if you cannot remember this, I will suggest you to reevaluate or to review the equations, the derivation that we did with the last lecture. To remember why we can augment the cost function, because this part equal to 0 at the optimal value. Because this part is equal to 0 at the optimal value. So at the optimal value, if we have this form, then we need to shift the equation into one side. So we ever did the same in the constraint augmentation problem. You still remember that, right? So here we did the same thing. So we shift this derivative to the other side. So this will be equal to 0. So we define this capital F. So if you remember this, then the following will be quite straightforward. The first equation will be lambda 1 multiplied by f1. So the f1 equal to this Vx multiplied this Vx minus x dot. So it's a Vx minus x dot. So this equal to f1. Because this one is actually our f1. So this is lambda 1 f1 plus lambda 2 capital F2. So capital F2 is given by Vy minus y dot. So plus lambda 3 with capital F3. So the capital F3 is given by this cosine u minus Vx dot. Our capital F2, these are our capital F3 plus lambda 4 multiplied by capital F4. So capital F4 is given by sine u minus Vy dot so this defines this lambda df. This is a lambda df. So it is 0. Remember we have a 0 at here because in our L equal to 0. Our L equal to 0 and this part we have the lambda df. So this multiplied by dt.